Hi. Hopefully you're not tired of seeing my face or hearing me talk, because for this lecture video, I'm talking about 3.2, Algorithms and Applications. So I know that this title is plural for algorithms and applications, but really we're going to focus on one specific algorithm. In particular, it's going to be called the augmenting path algorithm. What we're going to be doing today is, if I have a matching, how do I know if it's a maximum or maximal matching, maximal with an AL, matching or not? How do I know that I have the best option for my matching? That's a common question that we have in graph theory. How do I know I have the best possible option? So I'm going to go ahead and show you the details of the augmenting path algorithm. As per usual with all of our algorithms, it's going to look like a lot of very formal text. I'm going to hit you with a whole wall of text in a moment. So the augmenting path algorithm. So the input says we're going to input a bigraph with a matching M and a set of M unsaturated vertices in X. So again, I have some bigraph and I have a matching. How do I know if this matching is maximal or not? And I just noticed a typo here. This should not have a parentheses. That should be just a bracket. So I ignore my mistakes. So our initialization here is we're going to set S to be the set of M unsaturated vertices and T to be the empty set. And then, as with our normal algorithms, we have the special iteration that we'll repeat over and over again. And again, the result of this algorithm will tell us, do I have a maximal matching or do I have a non-maximal matching, which implies that I could make my matching even better. So, to look at this, let me show you the idea behind this algorithm. I do recommend that you take a moment to read this a little bit formally, but I'm going to talk about it more in layman terms. So let's say that I look at a graph and I have a matching for it. How do I know if this is the best matching? Well, if I look at this, notice that what I've drawn here is an augmenting path, AUG. Remember, an augmenting path is a path where the endpoints are not saturated by M. So you can see here my matching is the edge in the middle, and these other two are my remaining edges of my M alternating, or in this case, augmenting path. This matching is not maximal, because why would I choose this matching whenever I can reverse my order and use this matching instead? If I use this matching, it's most certainly a larger matching. In other words, for the idea of this algorithm is that I'm going to identify if I have an augmenting path. If I do have an augmenting path, I can always improve my matching by just reversing the edges into their respective sets. So this is the main idea that we will be using. So let's go ahead and apply this to an example. Here I have some XY bigraph with a given matching M. You can see it here with the thicker blue lines. I want to ask, is my matching M maximal? And if it's not maximal, how can I improve it? Improve. So I'm going to run through the steps of the iteration of our algorithm. So iteration number 1. To start us off, our initialization step says, let S be the set of all vertices that are not saturated by M within X. So if I look at X, I'm looking for all of the vertices that are not connected to an edge of M, or are not incident to an edge of M. So if I look at X1 to X6, the only vertices that are unsaturated are X1 and X5. Again, these two do not have an edge of M. They're unsaturated by my matching. The next part of my iteration says, all right, let's arbitrarily mark one of the vertices of S. So Your choice may differ, so the way that you process this algorithm might look slightly different depending on which one you pick. For here, I'm just going to start off with x1 because, well, it's number 1. The algorithm states, after I mark this, here I'm going to mark it by circling it, I'm going to explore along the edges not in M. So here, if I explore along the edge not in M, I'm going to end up with the neighbor of y2. And I have to ask, is y2 saturated or not? Well, if I look at y2, y2 is saturated by this edge right here. Since it is saturated, my algorithm says, let's add the saturated vertex to T. Furthermore, any vertices that can be connected along M, we're going to add that to S as well. So if I look along the matching M from Y2, I end up at X4. My algorithm iteration tells me now we add that to S. I've just completed one iteration of this. Again, I arbitrarily marked something from S, and then I did some exploration based off whether my edge is in M or not in M. So now let's start with iteration number 2. Again, I look at among all of my vertices of S, and I'm going to arbitrarily choose one. I can choose X4 or I can choose X5. For the sake of my animations, I just chose X5. Again, you could have chosen X4, which is why your process and iterations might look a little different. So I'm going to mark X5 by circling it, and I'm going to explore all the edges not in my matching. In this case, I have 2 options. Let's start off with just exploring the left one first. On the left edge, here I can see I hit Y4, and I have to ask, is Y4 saturated by M? And the answer would be yes, I am saturated by M. We have this nice edge right here. Since Y4 is saturated, we add it to T. And pretty much the same thing for Y5 as well. If I go down to Y5, then I have that it is saturated by M as well. It is incident to an edge of M. So I can add that to T. And since these are in T, I can continue to explore along M. So, for example, if I'm going from X5 to Y5, if I follow M, I go to X6, which means I can add that to S. And I can do the same thing over here. If I go from X5 to Y4, and then Y4 along M, I end up at X2, which tells me I can add X2 to S. Again, I'm using this idea of my alternating paths. I'm going back and forth between edges not in M and then in M. Alright, so this completes my second iteration. Now let's move to our third iteration here. Okay, so I have 3 remaining vertices in S that are not marked. Again, I can arbitrarily choose one. So let's arbitrarily choose X4. Again, I could have chosen X2 next or X6. The order does not matter in the long run. I'm just saying that let's arbitrarily choose one. So X4, I have to look down along any edges that are not in M. So if I'm working at X4 and I'm looking for edges not in M, I can move down directly. Its neighbor is Y4, and then I have to ask, is Y4 saturated by M? Well, Y4 is saturated by M, so I would add it to T, but it's already in T, so it's not really doing much for us. Y4 is already in T, but I'm just tracing my steps here. And then if I wanted to be repeating the algorithm strictly, I should be looking at Y4 and moving along M and adding its neighbor to S. But we've already have X2 and S. So this iteration 3, we went through, it didn't really do much for us, but again, we're just covering our steps and saying the order that we choose and mark our vertices doesn't really matter as long as we're being careful. So we have iteration 3, it didn't really change anything or even give us any new information. All it really did was just mark x4. Let's move to iteration 4. Again, I arbitrarily mark one of the remaining vertices of S. Let's choose x2 this time. If I look at x2, I'm going to move down to y via an edge not in my matching. So if I want to follow along an edge not in my matching, I'm going to follow this highlighted edge here. And then I have to look at y3. Is y3 saturated by M? Well, let's see, y3. y3 is not incident to any edge of my matching. Since y3 is not incident to any edge of my matching, first off, I cannot add it to T. T was reserved for those that were saturated. Furthermore, my algorithm earlier stated if I run into a situation where I have an unsaturated neighbor, this tells me I have to terminate my algorithm. And furthermore, this tells me that my matching M cannot be a maximal matching. So we now know that M is not maximal because I ended up with a vertex that was not saturated. So now, how do I fix this? I've completed my algorithm. Now the question is, how can I improve my matching? Again, if I'm not maximal, that implies that I can add more edges to this somehow. So I'm going to clear this up here. Notice I still highlighted this edge that we were working with. I'm going to go ahead and backtrack and identify an M alternating path. So again, we found this from going x2 to y3. So we're going to backtrack. So y3 to x2. And then if I want to alternate, I have to go along this blue edge to y4. And then, again, alternating, I have to go along an edge not an M. So I have really two options here. Again, the choice ends up being completely arbitrary, which is why your answer might be a little bit different than mine. For my slides here, I chose this edge on the far right. And then notice here that I can no longer alternate my path. I can't go back to M. So I've highlighted these three edges. What do we notice about these edges I've highlighted? If I look at these three highlighted edges, it forms an augmenting path. So if I started from y3, moved along these edges and ended at x5, x5 and y3 are not saturated so far. Remember that picture I brought up in the way beginning? If I have an augmenting path, we can always make it into a better matching by reversing our choice of edges. So right now, again, y3 to x2 and y4 to x5 are not in my matching, whereas x2 to y4 is. We're going to reverse those. So like what I have here. I went ahead and I reversed my matching. Now y3 and x2 and y4 to x5 are in my new matching. Let's call it M prime. So I'm still a matching here, and now I have an even larger matching. And this is just me clearing up the screen with the highlights. So this is definitely a bigger matching. But is this necessarily a maximal matching? Well, that's something that we had to check again. I have a new matching. If I want to check if this is a maximal matching, I would have to apply the entire augmenting path algorithm again. If I end up where I end up with an augmenting path, I can improve it. If that's not the case, then I must have a maximal matching. Sorry. Alright, so this is the concept behind what we would do for the augmenting path algorithm. And actually, that's all we're going to be covering for this section, largely because this algorithm is a fair bit to take in whenever you're seeing it for the first time. But besides that, I'll see you for the next set of videos.